Good morning, everybody. I am going to talk to you today regarding the critical components of liquefaction systems. Now, what we will be discussing in this topic is the following. We will try to introduce the critical components. Those are heat exchangers, compressors, and expanders. Now, we know very well that if we want to do a liquefaction of a particular gas, obviously there is a need for a suitable heat exchanger which can exchange heat from a hot fluid to the cold fluid and vice versa. The compressor is required to raise the pressure of the system from ambient pressure or atmospheric pressure to whatever value you would like to have. The expanders are those which are useful for carrying out adiabatic expansion so that the gas can get cooled. So you are able to produce low temperature of the gas. Okay. Under the heat exchangers, there are several types, and we will also discuss Georg-Hampson heat exchanger and Collins heat exchanger. There are also additional heat exchangers which are known as plate fin heat exchangers. We will discuss the heat transfer coefficients and friction factors of the heat exchangers. We will discuss the effectiveness NTU approach for the heat exchanger efficiency. We will talk about the compressors, reciprocating types, and rotary type. Also, we will talk about the expansion engines or expansion systems, both reciprocating type and the rotary type. Okay. So these are the points, these are the topics which we will be discussing today under the critical components of heat transfer. As I mentioned earlier, you see, we have for the liquefaction of a gas, several components are critical towards their functioning. Some of them are the heat exchangers, the compressors, and the expander. Of course, Joule-Thomson expansion valve is also another important component, but we will only inform that in brief about the Joule-Thomson valve in this lecture. Okay, heat exchangers transfer the heat or the cold between two streams of flow, namely the high and low pressure streams. The idea of having compressor is to increase the pressure of the working fluid from the atmospheric pressure to higher values as required for the liquefaction system. On the other hand, the expander expands the gas from high to low pressure to produce the cooling. Now, the coefficient performance of the above components are very important, and they have to perform to their maximum efficiency to obtain the liquefaction in the liquefier. Okay. Let's start with the heat exchangers. Now, heat exchanger is one of the prime component of a liquefaction system. Its primary function is to conserve the cooled that is produced, and also remove the energy from the compressed gas by transferring to the low pressure gas. The heat exchanger should be prepared such that its heat leaks are minimal. Okay. Without effective heat exchangers, obtaining low temperatures will be quite difficult, and there are several possible configurations of heat exchangers. So kindly look at the diagram on your right side, and you can very clearly see that there are different type of heat exchangers. A very simple heat exchanger would be to have a high pressure gas entering through a smaller diameter pipe and the low pressure gas coming out through a larger diameter pipe. So this system is called tube-in-tube heat exchanger because one tube encloses the other tube. Okay. Now, always the high pressure is chosen in the smaller diameter tube and the low pressure will go into the bigger diameter tube. Okay. We can improve this configuration to a slightly different perspective. We can add more number of tubes in the same enclosure of the low pressure tube. So we can have multiple tubes inside multiple high pressure tubes in a larger diameter low pressure tube. So this is another configuration of the heat exchanger. To increase the heat transfer, one can add additionally a wire in between the high pressure tube and the low pressure. That is the interspace between the high and low pressure tube. You can introduce a wire, and this wire can make sure that your heat transfer is improved because of turbulence. Okay. So there is another option possible, that what you can do is you can have multiple sets of tubes arranged in the form of a hexagon, and this entire bunch of tubes can be soldered together, or you can do what is called the dip bracing, so that this heat exchanger, the tube can now function as a total heat exchanger. The innermost tube will carry the high pressure fluid, and the outer tube will now carry the low pressure gases. Okay, so there is a very good heat transfer between them. Now, in place of wire, for example, one can also use fins, and the fins can improve substantially the heat transfer between the inner tube and the outer tube. Right. Okay. Let us move on to another type of heat exchanger, which is the Georg-Hampson and Collins heat exchangers. Now, Georg-Hampson heat exchanger is actually, it is a carefully spaced helices of small diameter tubes for the high pressure stream. So you can think of multiple number of tubes which are wound in the form of a helix, okay, and they are all joined together at the upper end and at the lower end, okay. This entire set of tubings ought to be wound over a large diameter cylinder, and this large diameter cylinder is enclosed by another insulated cylindrical jacket, and the spacing between the cylinders, between the two cylinders is should be quite uniform, and uniform spacing is absolutely essential to make sure there is a proper heat transfer between the low pressure stream and the high pressure stream. The low pressure stream flows over the helical tubes in the space between the innermost tube and the outer tube of the jacket. Okay. Now, this sort of heat exchanger will have end connections wherein multiple tubes will be joined together. So in other words, you will have bundles of tubes which will be joined together at the ends, and they will form a total high pressure output. Similarly, inlet also will have similar bundling of the tubes, and a jacket, a zone where the input stream is distributed to the smaller diameter tubes. Okay. Now, this sort of heat exchanger is used in the air liquefaction systems, or all the liquefaction systems relating to air, nitrogen, argon, oxygen, etc. And this heat exchanger is very efficient in performance. Okay. Now, Samuel Collins developed a unique extended heat exchanger, which has a large surface area, and this was used by him in his commercial helium liquefaction plant, which was used for helium liquefaction. Now, this consisted of 4 concentric copper tubes with the edge wound copper helix in the annular spaces. So you can see in the picture, there is an innermost tube, and then surrounding that there are multiple tubes, one over the other, and the number of tubes surrounding can be sufficiently large. And this is a cutaway section, as you can see here, and this is the top view of this whole system. And the innermost tube carries the high pressure, whereas the other annular spaces between the tubes carry the low pressure gas. Okay. Now, the helices act as fins and also extend the heat transfer area. High pressure stream flows through the innermost tube, and the other streams, low pressure streams, are all passing outside this. Okay, this heat exchanger had a very good performance because of the fact that there is a large heat transfer surface available due to the fins which are present over and each set of tube outside each set of tubes. Okay, there is another type of heat exchanger which normally people come across, and that is called a plate fin heat exchanger. When the space in the design is a premium, you use this type of heat exchanger. So what it has? It has a corrugated aluminum plates. The aluminum plate is corrugated such that, and you can see here the arrangement of the corrugation. So for example, here you can see the something like a zigzag formation of the aluminum, and this zigzag formation aluminum will be covered both on the top, bottom, and on the sides by appropriate closure plates. Now, when you do this, then what happens is you now generate two channels. The channel in the upper space, okay, between the plate and the corrugated material, and similarly, you also generate another space between the bottom plate and the corrugation. Okay. So now the gas can flow through the corrugations. One gas can flow through the corrugation on the upper side, as well as another gas, return gas or opposite gas can pass through the lower corrugations. Okay. Now this, because of this flow, there is an the gas can interact very well in between the heat exchanger plates, one on side, one on the other side. Then due to that, there is a very good heat transfer that is taking place between the two sides. Now, heat exchanger surfaces are formed by depressing the aluminum plate with the corrugated aluminum together, and many possible configurations are there. What we discuss is only one such possibility. There are multiple type of configurations possible, and some of the possible configurations are shown in the photograph given below. Okay. Now, this type of heat exchanger is now available for use in all our cryogenic zones. People use these type of heat exchangers for the liquefaction plants because they are quite efficient and provide large heat transfer surface. Okay, when we talk about the heat transfer, now we have to come out with heat transfer coefficients, okay, to relate to the performance of your heat exchanger. Now, there are also number of other coefficients which one normally come across. One of them is, some of them are listed out here. I'm not going to do any derivation or anything, but just want to give you an idea of the different type of heat transfer, different type of numbers which one encounters in the fluid flow. For example, one comes across what is called the Prandtl number, which is mu Cp by Kt. These are all dimensions number. NPR, which is the Prandtl number, it is equal to mu Cp by Kt. And Coburn J factor, again, is another number. JH is Hc by Gcp and multiplied by Prandtl number to the power 2 by 3. Okay. And Hc is the film coefficient of heat transfer. G is the mass flow rate per unit free flow area, and Cp is the specific heat at constant pressure. Okay. And Prandtl number is again, mu is the viscosity, Cp is the specific heat at constant pressure, Kt representing the thermal conductivity factor. Okay. Nusselt number is given by Nu, N of Nu, which is Hc dE by Kt. Hc represents the heat transfer coefficient, film coefficient, and dE is the effective or equivalent diameter of the flow passage, and Kt is again the thermal conductivity. we come across what is called Reynolds number. Reynolds number is N Reynolds is dEg by mu. In other words, dE is the equivalent diameter of the flow passage. G is the mass flow rate per unit free flow area divided by mu, which is the viscosity. You can also have Reynolds number as written as rho Vd by mu, and both will be the same. Okay. Right. Rho V is equivalent to your flow rate G. Okay. Mass flow rate G. Right. Now, there are a lot of correlations available for the laminar and turbulent flows, and these are all given in the Randal's-Barron's book. Kindly have a look at them if you would like to do some calculations. Okay, there are basically two approaches for heat transfer design. The approaches are relating to what is called the effectiveness NTU approach, and another approach is called the log mean temperature difference or LMTD approach. Both the methods are same, but just involve the different arrangement of parameters. Now, imagine that you are having a heat transfer occurring between two fluids. Okay, so we can think of the heat transfer in between the two fluids, and the two fluids are separated by an insulating wall. And let us assume that the wall temperatures, their end temperatures are, for example, you can imagine here, for example, this diagram, kindly have a look at that. Okay, the end temperatures are TH and TC. And now, if you have a heat transfer area A, then the heat transfer that will happen is given by the simple formula Q is equal to U A TH minus TC. It's because the heat transfer is proportional to the available surface area. The more the surface area, more will be the heat transfer. It is also proportional to the temperature difference between the two surfaces, and therefore it is proportional to TH minus TC. So we can introduce a constant U in between, which is effectively the heat transfer coefficient. So Q dot is equal to U A into TH minus TC. Okay, now in the case of a heat exchanger, now the fluid is flowing from one end to another end. One end will be the hot end, another one will be the cold end. Now, two fluids are flowing. Let us say one end will be starting. There are two channels available, and from one channel, hot fluid is flowing. Let us say the hot fluid is flowing from the left end to the right, and the cold fluid is flowing from the right end to the left. This type of flow is known as counter flow for the fluid. Okay. So in such a case, what we can do is we can try to select a small section of this heat exchanger and then look at what sort of heat transfer that takes place between the two streams. So that's exactly what we are going to do. Now let's consider a small section, with, let us say, is dA, a small section, and the heat transfer area is, let's call it as dA. Okay. Now the hot fluid is going from left to right, and cold fluid is flowing from right to left, and there is going to be a heat transfer between these two. Okay, the hot fluid is going to add heat to the cold fluid, and that value, let's call it as dQ dot. And similarly, the cold fluid is going to receive this sun, and that's the same as dQ dot, because we cannot, we have to have the energy conservation, and therefore dQ dot is the hot fluid what is giving to the cold fluid, and cold fluid is receiving the same. Now, what we can do is we can write, so because of this additional heat that is coming into the picture, there is going to be a small temperature rise in the case of the cold fluid, and there is going to be a small temperature drop in the case of the hot fluid. So we can write dQ dot is equal to minus CH into dTH. So there is a loss of heat from one to the other. So it is actually the thermal capacity part, which is capacity rate of the hot fluid, which is coming into picture. So also in the case of cold fluid, you will have minus Cc dTc. Okay. uh, the net heat transfer between the two fluids can be also represented in terms of the temperature difference. So we can write dq dot is equal to u dA into, we are considering a small sectional area, so u into dA into Th minus Tc. Right. Now we can consider, we can obtain the relation, we can subtract dTh and then dTc. So that is nothing but d of, Th minus Tc, which is, if you write the corresponding equations for the hot and cold fluids thing, then it will be nothing but dq dot into 1 by Ch minus 1 by Cc. Now this can be integrated, okay, so that you can get the value of Th minus Tc. It can be integrated from the temperature difference at the left end to the temperature difference at the right end. And the temperature difference at the left end will be Th1 minus Tc2. Th1 is the temperature of the hot fluid at the entry point, and Tc2 is the temperature of the cold fluid at its exit point. This is the inlet temperature difference of the inlet flow. What about the temperature difference of the outlet flow? It is Th2 minus Tc1. Th2 will be the temperature of the hot fluid at the exit end, and then Tc1 is the temperature of the cold fluid at the inlet, at its inlet end. Okay. Therefore, if you substitute this, then you get integral dTh minus Tc by Th minus Tc is minus of 1 minus Ch by Cc into u by Ch and the surface integral of dA, 0 to A, surface at dA. So you can, after some simplification, you get the relation Th2 minus Tc1 divided by Th1 minus Tc2 is equal to exponential of this particular term. Now, you can see the different possible configurations, different possibilities of existing. So, for example, in the case of a condenser reboiler type of situation, you have the hot fluid at one temperature, cold fluid at another temperature, and you have the constant behavior, right? Now, maybe in one case, one of them is having a B, in the configuration B, only one fluid is condensing or boiling, okay, hot fluid condensing, but the cold fluid is not. It is just maybe at a different temperature level. So you can have the two other configurations possible for the type of flow between inside the heat exchanger. Now, suppose both the fluids are not condensing, they are only cooling down. Then you have the configuration of this type. This is what you call the counterflow heat exchanger. And this one is known as the parallel flow heat exchangers. Okay, in the parallel flow heat exchanger, initially the temperature difference is very large. Both the fluids are running in the same direction. And then finally, when the liquid comes close to each other, there is a temperature difference which is very small. Okay, so these are the possible, the type of flows that happen inside a heat exchanger. Now, we have got an expression for Th2 minus Tc1 divided by Th1 minus Tc2 in terms of the heat transfer coefficient and the heat capacities of the fluid flows. Okay. Now, let us say we'll assume that the hot stream has a low heat capacity, low capacity rate. So we can write, now I'm saying rate is because of the fact there is a mass flow rate for the fluid, right? So mass flow rate multiplied by the specific heat will give you the heat capacity rate. Okay, that we have seen in the earlier slide. You can see here C is nothing but m dot Cp. So therefore, it is the mass flow rate term which is coming into picture here. Okay. Now, Ch is equal to Cmin and Cc is equal to Cmax. Okay, in that such a case, we can rewrite the expression as Th2 minus Tc1 divided by Th1 minus Tc2 is equal to exponential of UA divided by Cmin multiplied by 1 minus Cmin by Cmax. Okay. Now the number of heat transfer units is given as UA by Cmin. And the Cmin by Cmax is called the ratio, heat transfer ratio. The CR is a sort of ratio between the Cmin and Cmax. So now we have to estimate what is the heat exchanger effectiveness. What is the heat exchanger effectiveness? It is given by the relation. It is nothing but the actual energy transfer that is happening to the maximum possible energy transfer that can happen in a heat exchanger. Now let's look at the maximum possible energy heat transfer. The maximum possible energy for heat transfer will be C min multiplied by TH1 minus TC1. Okay, they are the ones which are at the extreme temperature differences. TH1 is the temperature of the hot fluid at its entry, and TC1 is the temperature of the cold fluid at its entry. So that will be the maximum values, that temperature maximum values, maximum value of the temperature difference. And if you multiply by C min, that will be the maximum possible energy transfer. Okay. Now in such a case, epsilon can be written as CH TH1 minus TH2, because what happens is your hot fluid losing certain amount of energy. Okay, its heat capacity rate is CH, and TH is initial temperature TH1 to final temperature TH2. So therefore, how much is the energy transferred by the hot fluid is CH into TH1 minus TH2. This should be divided by C min into TH1 minus TC1. This is equal to, you can explain not necessarily in terms of the hot fluid. You can also write the same relation in terms of cold fluid. For the cold fluid, it will be Cc multiplied by Tc2 minus Tc1. Okay, that will be the value for the cold fluid. Okay, so now you have to divide this by C min into Th1 minus Tc1. So now this will be what is called the efficiency part. So epsilon is the heat exchanger effectiveness, and you can modify this expression. You can rewrite this expression in terms of NTU, right, as epsilon is equal to 1 minus exponential of minus NTU into 1 minus CR. CR representing the heat capacity ratios between the hot and cold fluids. Whole thing divided by 1 minus CR exponential of minus NTU into 1 minus CR. Okay, this is the effectiveness of the heat exchanger. Okay. Now we can consider two cases of interest. One is what is called the balanced operation. Another is what is known as the phase change condition. In the case of a balanced operation, the capacity ratios between the hot and cold fluids is the same. It is equal to 1. That is, the capacities of hot and cold fluids are the same. Therefore, C min by C max is equal to 1. Okay. In such a case, you can simplify the above expression, and heat exchanger effectiveness now can be shown to be epsilon is equal to NTU divided by 1 plus NTU. Okay. Number of heat transfer units divided by 1 plus number of heat transfer. Now, in case you encounter a boiling or a condensation of one fluid, okay, on one side of the surface, then what happens is your Cmax tends to infinity. The heat transfer at that time, because of the condensation, it is infinity. And so in such a case, you are dividing, CR value has to be 0, because CR is nothing but C min by Cmax, Cmax being infinity. So CR is equal to 0. So if you use this condition, then you get epsilon is equal to, which is the heat exchanger effectiveness, equal to 1 minus exponential of minus NTU. That's what you get. Now, these are the general expressions that you get for determination of heat exchanger effectiveness. Okay. Now, we can consider the same thing for different arrangements of the heat exchanger. For example, there can be parallel flow, that is flow in the same direction, or you can have counter flow in the opposite directions and so on. The expressions in the case of parallel flow, for example, is given by epsilon is equal to 1 by 2 into 1 minus exponential of minus 2 nu. This is the case where Cr is equal to 1. In case there is a condensation and boiling on one side for a parallel flow heat exchanger, then we get epsilon is equal to 1 minus exponential of minus NTU, the same as the other case. And in this case, Cr is equal to 0 because of the boiling or condensation on one side. Okay, so far we have discussed the heat exchangers and its effectiveness, and this becomes useful for us whenever it is needed to determine the effectiveness of the heat exchanger. Okay. Now let's look at the another component for heat transfer, another important component in a liquefaction system. This is nothing but compressor. The job of the compressor is to convert the low pressure gas into a high pressure gas. So there are two types of compressors which can be generally used. One is called the reciprocating type of compressor. It means the gas, a small quantity of gas is taken in a cylinder, and then it is compressed by a piston by moving the piston from, let's say, far off distance, and then you reduce the volume of this so that pressure increases. So this reciprocating type of compressor, okay, uses a piston cylinder arrangement, and generally they are quite suitable for pressure ranges from 4 megapascal to about 20 megapascal. In other words, it's equal to 40 bar to about 200 bar. Okay. Okay, this is the sort of pressures that it can be handled by a reciprocating type of system. Now, in a typical reciprocating system, you will have a piston cylinder arrangement, you will have a crosshead, okay, and then which will be moving the piston forward and backward because of this crosshead arrangement by any rotary mechanism. Okay, so for example, a typical reciprocating expander is shown here in this diagram. As you can see, the piston is moving within this zone, and the rotary motion of, let us say, a crankshaft is converted to the up and down motion, the reciprocating motion, by the use of an appropriate crosshead, etc. Typical steam engine, for example, would use this type of expanders. Okay, the reciprocating expanders. Now, in place of reciprocating expander, one can also use screw compressor systems instead of reciprocating expander. Now, the rotary expanders, these screw compressors belong to rotary system, and they are very much suited for a large flow rates. For example, in the case of a reciprocating system, a small quantity of gas is taken inside a compressor at some low pressure, and then because of the movement of the piston, the gas is now compressed, and then the pressure increases to higher values. Okay. Whereas in the case of rotary system, they are suitable for large flow rates, but pressures may not be very large. Okay, how do they do that? They use by using screw compressors. In a screw compressor, there are two screws which are touching each other, but the dimensions are such that whatever gas that is trapped in between them, okay, as the screw moves, rotates, it is actually, the gas is getting compressed, and by the time it reaches the other end, the gas is compressed gas. Okay. Now, these sort of systems are being used in liquefaction plants, and the screw compressors are normally suited for large mass flow rates, but not very high pressures. Okay. In place of these type of compressors, one can also use what are called scroll compressors. In the scroll compressors, there are two scrolls, rotating scrolls are there. One static scroll, against which another scroll is rotating, which is the rotating scroll. The gap in between the scrolls will carry the gas. Okay. As the scroll rotates, the low pressure gas gradually gets converted to high pressure gas, and at the exit, choosing appropriate valves, the gas will be transferred to a high pressure zone. Okay. Now, as an example, we have said steam engine type, where the crankshaft and crosshead are housed in a separate enclosure. These are reciprocating system. The internal combustion engines, which we normally have in our two-wheelers and so on, they are also of similar type. In this case, they are enclosed. The internal combustion engine are enclosed in the same casing as that of the piston. There are non-lubricating type of systems are there, and they are very much non-lubricating type systems are very much attractive. Okay, where they use a leather sort of arrangement, a cup, so that the gas is not contaminated from the oil of at the bottom of the enclosure. Okay. Next, we try to discuss about the rotary type of compressors. In the rotary systems, the systems can be either impulse or reaction bladed or radial flow type, inward and outward type of systems are used. For example, here we see a rotary expander, what is shown here in this case. Okay, you see the gas. Oh, I think I have to just mention briefly about the expander parts. This slide. Yeah. Okay. I will just talk about the expander first. In the expander, actually we have the gas is coming in and it has to be expanded to, the gas has to be expanded to low pressures so that it produces gas, now does work on the environment, on the either the piston or a rotary blade, so that the gas gets cooled. Now, for the rotary expanders, there are multiple systems that are possible. Okay, one system can be a piston cylinder arrangement. A small quantity of gas is trapped and then it is expanded. Okay, so this is one possibility. And you can also think of an alternate arrangement in which the gas is continuously expanded using a rotating machinery, maybe a turbine blade and so on. So, for example, a typical rotary type expander is shown here in this diagram. Here the incoming gas, whatever that is coming in, okay, and the gas is entering at some point here, and the gas, because of the motion of the rotational motion of the turbine, the gas is expanded, and the expanded low pressure gas is passing out through this. Because of the process of expansion, there is a certain amount of work output in the process. This work output is actually used for compressing a gas at the opposite end of the crankshaft, where a compressor blade is also attached. So you get a high pressure gas at the exhaust point on this side, and the compressor discharge will now be having a high pressure. So on one side of the system, you have the expander, the opposite side of system, you have the income. Okay. Next. Now, there are other expansion engines which have been done in the earlier times. For example, for the ice making machines, as early as in 1849 by John Gorey, he also used an expansion engine. The very first expansion engine was built by George Claude in 1902 for air liquefaction. He used a leather cup as a piston seal, and ran the total thing unlubricated. So the leather will move up and down, and then the gas will be expanded because a small quantity of high pressure gas is trapped and suddenly converted to low pressure. So therefore you get an expansion of this type. Okay. Now Haaland actually made further improvements on whatever that was done by George Claude. What he could do was he increased the length of the cylinder so that all the sealing problems are encountered only at room temperature, because it's easier for us to deal with these problems at room temperature condition. And this is possible by just expanding the length of the piston. Okay. By the same guidelines, Collins made the very high efficiency expander piston. This was free to align by itself. Okay. So this variability was improved by the use of micarta sleeve on the piston. This was what was done by uh, Samuel Collins. And he also did piston valve arranged rods are enclosed in a thin cylindrical chamber of stainless steel. Okay, you can see in the picture, the two parts are shown. The Haaland system compressor part, I mean expander part is shown here. So you have a gas which is trapped here, and then this is a low conductivity, low thermal conductivity cap, and then the gas is suddenly expanded. It produces cooling of the gas. This is the Haaland system. And this one, what you see here is the arrangement of piston cylinder arrangement of Collins, where you have a micarta sleeve on the system, on the piston, on the top. And this moves up and down um, because of the gas is trapped here and then expanded. Because of the expansion, you produce cooling of the gas, and this also is the movement of the piston up and down is also connected to an appropriate cam arrangement so that the inlet and exhaust valves are properly opened. Right. So this is one of the marvelous expansion uh, system which has been developed by Samuel Collins, which is being used even till date by many fabricators, many suppliers of the cryogenic plants. Right. I think I will stop here because these are the various components which we are supposed to, critical components for liquefaction. So thank you very much for your patient listening. And we will now go over to the new topic in another lecture. Thank you. Thank you once again.